Hi, my name is Nicholas Buckberg. This is the Bearmax 2.0 presentation for Group 28. I'm a mechanical engineer, along with Bhavani Sivakumar, and our team also includes Rahim Khan, who's a computer engineer, and Zachary Larson, who's also a computer engineer. Bearmax is a social emotional learning robot designed to be able to detect, analyze, and perform emotions for the purpose of therapy to children on the autism spectrum. The main way we hope to accomplish this is through the implementation of an emotion game where the Bearmax is able to copy the emotion of the child. Currently we have 8 emotions: happy, sad, angry, confused, shocked, worried, scared, and disappointed. And Bearmax will be able to act these out. For example, if a kid goes to act happy, Bearmax will detect that and then repeat the happy emotion. This is our current progress. We have finished the skeleton. The PCB has been designed, but we're having issues. The skeleton at this point, aside from some minor tightening and adjustments, we will not be working on further. We're now more working on the software electrical side and integrating with the computer science team, which we hope to accomplish within the next few weeks. These are our Bearmax specifications. We had a goal of greater than 1 mile an hour and less than 5 miles an hour initially, but just having it be greater than 1 mile an hour was satisfactory for what we needed. And our tested value is around 1.2 miles an hour. All of our ranges of motion for the motors and joints were met, which will be further explained in a following diagram. Right now the weight is currently 6.2 pounds with the full skeleton, but that does not include the Jetson, Arduino, and the shell, wiring, things like that, but we imagine it will not add 24 pounds. So weight-wise, we're in very good shape, but we won't know the full weight until it's fully finished. Bearmax current height shouldn't change, so around 2 feet to 2 1/4. The PCB, we're currently having some issues with the power output to the rest of the robot. It worked in testing, but when fully hooked up to the robot, we started having issues, so that will have to be troubleshooted, which we're currently doing right now. A volt supplied by rechargeable battery, no issues with a rechargeable battery, and the time to display emotions from Jetson prompts, that will not be able to be recorded until we start testing after integration. This is our range of motion diagram. These are all the different joints and motors for the robot, along with their specified ranges of motion. The ones at the bottom for the DC motors aren't as important because they're just moving forward, so the 360 degrees doesn't really have a bearing on the emotional detection or emotional expression. But it met all of the requirements. So this was our demonstration for just the torso, but the way that each of the surfaces were tested was using a servo tester hooked up to a 6-volt power supply, or 6-volt battery supply. So it just goes through the full range of motion, which you can see the gears are turning right here, turning the PVC pipe. Overall, the servos met our necessary ranges of motions and requirements, so no issues there. It's just a little test with weight on it. Speed testing, we did 10 trials, recording the over a set distance, recording the times, and then calculating the speed, and then converted it to miles per hour, which is how this was determined. Overall, we were over 1 mile an hour, so we don't have any issues there.
Bearmax's dimension specifications are shown in these 2 images of the side and front view of the skeleton. Bearmax's total length or span is about 1.5 feet at rest, 10 inches in depth, and approximately 2 feet in height. This is an isometric, full-defined view of the skeleton of Bearmax, showing significant components such as the head, neck, shoulder, arms, hands, and torso. It also shows the robot mounted to a modified pre-existing track system. This track system will also house components such as the battery, Arduino, and Jetson Nano. The neck-shoulder connection is one of the parts of concern with the design due to not only having one anchoring place to the main body via the neck, while simultaneously supporting components such as the arms and hands, which are admittedly heavy. Since this part is of concern, for the purpose of failure modes and effects analysis, we decided to run a SOLIDWORKS simulation. The orange on the two back holes represent fixed points of the part, since the part will be bolted to the neck piece. Next, a distributed load was added to the upper surface of the shoulder piece to represent the weight of the components, such as the arms and hands, as well as the weight of the shell that will be draped onto that piece, and potential weight a user might put on Bearmax during an interaction. We decided to place 10 newtons of force on this piece, which is equal to roughly 1 kilogram in weight. This is approximately how much all of the components, including the motors and portion of the shell connecting to this component, will weigh. As you now see, some buckling is starting to occur as a result of that load, with the displacement graph showing the different colors and ranges of where it is more likely to fail, with the red aspect being the most likely to fail. The warmer the colors, the greater likely it is to fail at that specific point and give away at that specific point due to that shear stress. The von Mises diagram is to show the area of shear fracture, which is another type of fracture that can occur, and that is near the mounting point, which is as expected. A way to mitigate this failure is by adding supports to this piece and connecting this piece directly to the bottom of the neck in order to distribute that load and force, so it's not greatly on the ends that are free floating.
So here is our PowerBoard printed circuit board design. It is a circuit designed to take in 12 volts from the power bank we will use, and it will distribute the necessary voltage to the Arduinos, the servos, the motor controller, and any other components. So starting from the bottom left, we see the output for the motors where 12 volts will go out. So this is specifically for the motor controller because the motors we use require 12 volts. This, mo this motor output is not attached to the voltage regulator. Instead, it's attached directly to the 12 volt input. That way, the motor controller can get 12 volts while the rest are just getting 5 volts. In the middle, we have the voltage regulator, which allows the circuit to convert the 12 volts to 5 volts for the components like the Arduinos and the servos. Then beside that is the input where the 12 volts will go in. This will essentially be where the power bank is plugged in. Then finally, to the right, we have the output where the 5 volts will come out. This will be for the servos and the Arduinos. And in there, it also includes some ground ports as well. Next, I wanted to do voltage tests of the printed circuit board. I wanted to check if the input voltage was actually 12 volts, and if the output voltage at the motor connector was 12 volts, and if the Arduino and servo connector outputs were 5 volts. As you can see, the input voltage at the power board was around 12 volts. Similarly, the motor connector's output voltage was 12 volts, and the Arduino and servo connector outputs were 5 volts. Next, I wanted to test how well the circuit would run during a 20-minute period. So I connected an input voltage of 12 volts, and to simulate it working, I attached a load and set it to 5 volts and 2 amps, which is approximately what the servos and Arduinos will be using. In addition, I wanted to check the temperature of the regulator to see how hot it would get. I, I wouldn't want the components to melt after all. So for every 5 minutes throughout the 20-minute period, I checked the temperature of the regulator, and it turns out the average temperature ended up being 40.48 degrees Celsius. that is well within the parameters as according to the datasheet. It is not, allegedly, it's not even close to how hot the regulator can be.
So this is going to display the happy emotion using an Arduino. We haven't fully integrated with ROS yet, so this is just for the purpose of displaying the motors. And there it is. So now we're going to get into the angry emotion display. Again, Zach will just hook it up to the power, and we'll see. Now, here we go. So it does move to the correct positioning, but there's some things we have to work through on the shoulder servos, but it does display the correct emotion.
So this is a block diagram explaining how the power system will work in general. We first have the rechargeable power bank at the bottom right. That will provide 12 volts of power to the power distribution board, and it will also provide the necessary amount of power for the Jetson. Now, luckily, it has multiple output ports. One will be dedicated to the PCB, the other will be dedicated to the Jetson. Now, the PCB will be able to distribute the necessary amount of power to any of the components, as seen in the previous picture. It will provide 5 volts to the Arduinos along with the servos and the LCD eyes. In addition, it will also be able to provide 12 volts to the motor driver.
So one of our main goals of Bearmax is to portray the different emotions. And earlier we defined 8 emotions, and here we have 8 poses to represent those emotions. Each of these poses has been given a short description, as well as how the pose could be described to a smaller child, using onomatopoeia, of course. The poses are created by assigning angles to the different joints of Bearmax, the different motors, and all the angles shown in the future slides are in radians. This is not one of the emotions, but just the neutral pose that Bearmax will assume upon starting up. You can see this 3D model. This was taken by taking the SolidWorks 3D model and converting it to something known as a URDF, which ROS can then use to define the joints and pose the robot for simulation. The first pose we have is the happy pose. You can see Bearmax has his arms up over his head. He's yelling yippee and hooray. The second pose you can see is sad. He's crying. He's wiping tears away from his face. The angry and mad pose, he's got his arms up and fists balled up. The confused and perplexed pose, he's scratching his head and cocking his head to the right. The shocked and surprised pose, you can see the hands on the cheeks. In the worried and concerned pose, has his hands at his face. He's thinking if he had a beard, he'd be scratching it. And then the shy and scared pose, you can see his hands clasped. He's turned away from the user, but kind of looking on in fear. And the annoyed and disappointed pose, it's when he's looking away. He's not interested in the user at all. We can see some of these being represented here as well. This is using the Arduino, and the poses aren't one-to-one, but this is an idea of how it would look like. The poses were then taken, the angles were then taken and put into the Move It Setup Assistant with ROS2, which allows us to store those movements and reference them later with the Move It API. Additionally, this generates something known as the collision matrix, which allows the robot to, during movement, detect if any of its limbs are colliding with itself. It additionally generates a matrix of limbs and joints that will never interact with one another and never need to be checked. These are the same poses from before, but now defined in the Move It Setup Assistant. And then finally, we have the test that we performed on our future plans moving forward for the last stages of our project. So far with the tests we've performed, we have the degrees of freedom of the motors, basically testing all the limits for the various motors, the arms and such, the chassis, etc. The weight capacity, how much weight the robot itself can hold, as well as the total weight of the robot skeleton will have been performed by this point. The PCB temperature test has also been performed at this point. And then finally, for future tests, we have the specifications to have it run for 20 minutes and continuously without power system failure or the logic shutdown. And then finally, the emotion poses that we've planned as shown before, but with the robotic shell. The shell will add some space around the face and the body of the robot, so we might need to give the arms more clearance for that. Then we have our future plans with integration with the CS team, specifically the emotion game, the sensory overload, as well as their app to collect statistics for the emotion game for a user. Moving forward, we have to design that robotic shell covering, planning on having a resin layer as well as a soft fabric layer. And then finally, for the robotics, we have the completion of the ROS nodes and components, which will then allow us to use Docker to containerize the whole application and deploy everything onto the Jetson.